in this course, uh, which is basically the extension of the real analysis in some sense. So, first definition in this course we have studied is the definition of topology. So, topology is nothing but a family of subsets of X which satisfy all the properties of the open set in the real analysis. In fact, it is also generalizes the definition of open set in Rn. So topology means on a given set X is a collection of subsets of X which satisfies these three conditions. Null set is in tau, X is in tau. It is closed under finite intersection. It is closed under arbitrary union. So we already know this definition and we have seen various examples. One of the main example is this which is known as Cophanite topology or finite complement topology, which we can define on any arbitrary set X. Whatever set X is given, we can define this topology on that. And other two topologies are trivial topologies. That is a trivial topology is phi and X, and the other simple example is the discrete topology, which we can define on every set X. So these three topologies are we can define on any arbitrary set X, and then we have studied the standard topology on real line. So that is the collection of the open sets that forms this tau. So in general, the elements of tau are called the open sets if tau forms the topology on a given set X. So once we in topology we have extended the notion of open set, and then we want to extend the notion of intervals of the real analysis. So for that we have discussed the definition of basis. So what is the basis? Given a set X, a basis is also a collection of subsets of X which satisfy these two properties, which we can explain uh, by a Venn diagram also. So what is the first property? First property is that suppose my set is X, then I take any element X in X, then I can always find a element B in this family such that X belongs to B. So that is first property. And through Venn diagram, we want to discuss the second property. Then it says that if I have X is element of X, which is belongs to two basis elements, so that B1 and B2. So B1 and B2 are elements of this family B, which is a subset of X. So that means B1 and B2 both are subset of X, both belongs to B. So whenever we have X belongs to B1 and B2, we can always find another set B3. So this is in the intersection, which contains which is subset of B1 intersection B2. So using Venn diagram also you can remember these two conditions. Of course, this X is not always R2. I'm just explaining using Venn diagram, so therefore I'm taking X in this way. It is not always X2. X can be any finite set also. So this is the definition of basis, and then we have checked that intervals on real line, they satisfy these two properties of the basis. And for R2 we need open disk. If I take the collection of open disk, then that has these two properties satisfied. Collection of all open disk, that means it is interior of the interior region of the circle. Open disk means what? It is a interior of the circle. So all these regions forms a basis. That means these two properties on R2. The same way we have
Sir,
also yes.
sir, can you please recall the first property for me?
First property is that for every element x in the set x x in the set x, I can always find element in the family B in the this family. So it is same as that we discuss real line x equal to r, then for every x, what we will take b in the case of real line, we will consider all the open intervals. So we know that every each real number x, I can always find an interval around that. So this interval AB is element of this family. So small b equal to a comma b. So I can always find a b such that x belongs to b, which is element of this family for every x in the given set x. So here capital X is R. So this is first property. And the second property is that if I have any point x in the real line and I have two elements of this family B, that means two open intervals which contains that point x, then I can find another element of V that is again open interval which is contained in the intersection of the first two open intervals. So open intervals satisfy this property, both the properties of the basis. So in some sense, in basis we are extending the notion of kind of intervals. And now in the previous lecture, what we discuss is that if I know that x is a given set and b is a basis for x, so that means this family B satisfies this both the properties. For every x there exists B belongs to B such that x belongs to B. That is first property. Second property is that for every B1, B2 containing x, point x, I can always find B3 belongs to B such that x belongs to B3 contained in B1 intersection B2. So both these properties are satisfied for the elements of B. That means B is a basis. Then can I define using B some topology on X? So that is this proposition. So what is this family tau B? Tau B we define to be the union of all the basis elements. That means all the elements of B, this family B. You take all the unions. So they are the elements of tau B. So tau B is defined in this way. Now we have to check that tau B is a topology or not. Tau B is defined using the basis, given basis. So this new family tau B, which depends on B, whether this tau B satisfies the three axioms of the topology. So first axiom is phi and x belongs to tau B, right? So that result we have discussed earlier. That if B is a basis, then tau B is a topology on X. So how we define tau B? Tau B we are defined actually in this way, not in the way I said earlier. So we are taking in tau B only those sets U which satisfy this property. So a set U belongs to tau B. If it's for every element of U, x belongs to U, I can find some element B in the this family B in this basis such that X belongs to that element B which is contained in this set U. This should be satisfied for every X in U. So this way I am defining tau B. And once we define tau B using this property, we can easily check that it contains null set, it contains the whole set X. If U1, U2, Un are finitely many elements of this set, then using this property of the set, we can actually prove that the finite intersection also belongs to tau B. So we discuss only using Venn diagram for n equal to 2 case, but then by the induction you can extend this argument for the general n cases. So this proof is given in the book also, so you can go through it if you uh, are not able to hear understand here. You can go through in the book. It is given, complete proof is given, but more or less the idea I have already mentioned here. So basically we are using the second property of the definition of basis B. And then the third property also we can prove very easily. In fact, this third property is very easy to prove. So what this result says in a simple language is that if I have a basis, I can define a topology on X. What this proposition says? This proposition says that if I am a given any set X and B is a basis over that set X, then if I define tau B in this way, then tau B is always a topology on X, and tau B contains phi, tau B contains X, so that is a non-empty collection of subsets of X. So we don't know exactly how many sets will be in tau B, but tau B contains all the sets satisfying this property. So it is defined using the property, not explicitly. But now the next proposition helps us to find it explicitly. So that is what we were discussing in the last lecture, that if I take X is any arbitrary set and B is a basis on this set X, then the tau B which we define in the previous proposition is exactly this set. So it is nothing but the set of all unions of the basis elements. So we were trying to prove this result. So let us recall what is tau B. Tau B is nothing but U belongs to power set of X, such that for all X in U there exists a basis element. That means B belongs to B, such that X belongs to B, which is subset of U. So this tau B, we want to show it is exactly this set. So this set I am denoting just using the notation tau B dash. You can call it capital A also, doesn't matter, right? It is just some set or a family. So we just want to show this set and this set are same. So therefore every element of this set is belongs to this set, and every element of this set belongs to this set. So that is what we want to show. So first thing we have proved is tau B is contained in tau B dash. That means if I take any u belongs to tau b, it belongs to tau b dash. So any element u belongs to tau b satisfies this property. So we started with that. We started with any basis element in B. So since any basis elements in B satisfies this property trivially, because you can take B dash to be B itself. So if I take here B dash, I want to check whether B dash satisfies this property. Then so what is B dash? B dash is element of the basis B, whatever basis is given, its element is B dash. And if I want to check that B dash satisfies this property, I have to find some B for this B dash. So I will take the same element B dash to be B. Clearly X belongs to B is containing B dash because these two are same sets, because B equal to B dash, right? So for every X in B dash this is true. That means B dash is the element of this set. So and once B dash is the element of this set, we take union of all such elements of B. It is also contained in tau B dash, right? Why? Because this is a topology from the previous proposition. The previous proposition we have checked that if I define this collection in this form using the basis given basis B, then it is always a topology. And the third property of topology says that if I have any two element or infinitely many elements of a topology, its union also belongs to topology. So here we proved if I have a basis element, then it belongs to this family, and this family forms a topology. So it is closed under arbitrary union. So this gives us the first inclusion. Now we are interested in the second part. So what is the second part? Second part is that we need to show that, so in short here we proved that union B alpha, each of them are the open sets. Open sets means it satisfies this property. So now conversely we need to check that every u satisfying the property so what is the property? For every x in u there exists b in b such that x belongs to b contained in q. So every such u satisfying this property can be written as, so this u should be of this form. So what is the another inclusion? If I want to prove this is subset of, This is subset of this. So that means I have to show that every u is of this form, right? Can be written as u equal to union of b alpha, where b alpha belongs to b. Yes, so what is the question? Any questions so far? Okay, so let me continue. So every open set, basically we want to express every open set in this topology tau v we want to express as a union of basis elements. So for that again we will use this property because we don't have any other information about this family. We know that this family satisfies this property only. So the proof of this converse is that since for every x in U there exists some b. Now this b depends on x. So I will call this b to be bx because it depends on x. And then we have x belongs to bx contained in U. Just I'm relabeling the set b as a bx. And this is true for every x in U. So that means what? Therefore, if I rewrite this again, what is this? This is singleton x contained in bx contained in U for all x in U. Now what I will take? I will take union of this x for x in U. So if I take union of all this set x belongs to U, then clearly it is a subset of union x belongs to U bx. And these sets are same. So you take U union U, you will get anyway U only. Right? As many times you take U union U, you will get the same set U on the right side. So we get this from the previous step. And then what is this set? Union of singleton x belongs to U. Yes, what is the answer? I could not hear. Yes, so that is the full set U, right? If I take union of the each element of the set, then I will get the same set. So this is exactly U. So just to differentiate, I am writing U in this way. Otherwise, there will be confusion with union. So this set is U, which is contained in the union of x belongs to U of Bx, which is contained in the set U. So this means what? From this, what we can write? A subset of B subset of C. Sorry, A subset of B subset of A. That means what we can say about A and B? They are equal set, right? So that is true. So this U is nothing but the union x belongs to U B of x. So this U in fact we can write as a uh, union of the basis elements. What is Bx? Bx is the elements of B. So that means every element U which satisfies this property, we can write that U as a union of the basis elements. Right, so here alpha is element of I. So we have to find some I here. So what is I basically here? I is nothing but U in this case. Index set is U itself. So therefore, we have proved the converse also. That means the other inclusion holds. So this is also true. So now this set is a subset of this, and this set is also subset of this. That means both the sets are equal. So what does this say? This says, and what is this particular set? That is nothing but tau b. That is the topology generated by the basis b. So if I am given a set X and B is the basis on X, then this tau B is not only the topology, but it contains the open sets which are nothing but union of the basis elements. This basis elements of this basis. So now, did you understand this result? Any doubt in this proof or the statement? Yes, so we will take the example, but the question is that this theory, did you understand? Anyone has doubt in this? Okay, so I hope everyone has understood the meaning as well as the statement. So again, let me go back to the statement. It says that I am a given set X and I have a basis B, then I can define the topology in this way, and the elements of the topology, which we usually call the open sets, they are nothing but the all unions of the basis elements. So if I know what is the basis, that means I know all the elements of the basis of this family B. Then if I take all the unions of those sets, then I will get this topology. So let me repeat it again. If I know the set X, if I know this family B, what are the elements of B, then to find this topology which generated by B, what I will do is I will take all the unions of the elements of B, right? I will take all the unions, all possible unions of the elements of B. That will be my topology. And all that the elements of topology are known as the open sets. So now let us go to this particular example. So what I have asked here, so we were discussing that if X is any set, finite, infinite, real numbers, R2, whatever, we know that we can define this basis on this set, whatever set is given. Right, so if I know the set X and I know the basis over that, so what will be tau b in this case? So by this proposition, if I use this proposition here, then it is nothing but the all unions of the basis elements. So from the proposition, what is tau b? Tau b is nothing but union of b alpha. So this means all the unions we are taking, right? Where b alpha is element of b. Now in this case, I know what are the actual basis elements. They are the singletons. So what will be this set? Can you tell me? If X is any set and the elements of V are singleton sets. and tau b contains all the unions of the singleton sets. Then what is tau b?
X.
So whether it will contain the set X, tau b contains X.
It is topology.
It is topology that we know, we have already proved. If I have a basis, then tau b is a topology. So that is a proposition we already proved. Now the question is, we
Okay.
want to find what are the elements of tau b explicitly.
X.
X is
Tau b.
element. So first trivial observation is that all the singletons are elements of tau b, right? All the singletons are elements of tau b. So in other words, if I want to write it again, what is B alpha? B alpha is the elements of B. So that means it is union of all singleton X. So here I am not using alpha. So basically union of X. X is in X. So now you tell me what is this set. If I take union of, suppose there are two elements X and Y in X. So does XY belongs to this set? Does XY belongs to tau B? Because tau B
Okay.
contains singleton X already. Uh, what is the answer? You can write in chat box also. So question is whether, yes,
I think it will be in set inside set.
it will be
Unique set inside to set. It means singleton X comma singleton Y. Then again braces means set inside a set. Means not like
no,
this
no,
X
no, no.
comma Y.
You see, what I'm saying is that if I know basis, what is the basis? Basis is the collection of all singleton sets. In tau B, I'm going to take union of the basis elements, means union of all these elements. So what are the possible unions of such elements? So if I know X, Y belongs to X, then can I write X, Y as a union of singletons? I can always write because it is nothing but singleton X union singleton Y. So that means it is belongs to tau B, right? The same way, if I have three elements, also we can write as a union of X, union of singleton Y, union of singleton Z. So now question is that can I write capital X also in this form? So I can write X also in this way. X belongs to capital X singleton X, right? So X is also belongs to this family. So that means basically every subset of X I can write as a union of singletons. So therefore this set is nothing but power set of X. So now is it clear what I want to convey?
Yes.
That every subset of X we can write as a union of the singletons. So therefore every subset of X is element of tau B. And since every element of X is element of tau B is power set of X because every topology is subset of power set of X. So we have shown every element of power set of X is in tau B and tau B is always subset of power set of X. So that means it is exactly power set of X. So in this example we have noted that if I take X to be any arbitrary set, yes, any doubt?
If elements, then how we express in singletons?
What you are saying, elements?
or more than two.
More than two, then there may be three elements, n elements. Suppose n elements is there, x1, x2, xn. So I can write is the set containing x1, x2, xn as singleton x1 union singleton x2 union singleton x3 union up to union singleton xn. Right? Even set of natural numbers we can write as in that form. So for example, I have set of natural numbers. How do I write this? Union n belongs to n singleton n. Right? Same way you can write z also.
So sir, this self cardinality is only equal to n, na? How it's equal to p of x is p of n?
Why you need cardinality? That is the question.
Because here we are is proving is equals to p of x.
So I'm saying that every element of px can I write as a union of singletons.
Yes, yes.
That we can write, right? And so that means what we have shown here is a is a sorry, a belongs to px. That means a belongs to tau b. So this we have proved. So that means what? This says power set of x is subset of tau b, right? And on the other hand, we already know that tau b is a topology. So tau b is a topology. In fact, tau b is defined as u such that u is a subset of x. So that is always subset of power set of x, right? So this is what I wanted to convey through this example. Okay, any other doubts you have?
Yes, sir. One question. This basis you have singleton x on the topology. Its power set of x means discrete topology. So if the basis is unique, or there will be other basis on this discrete topology.
Uh, oh, basis. Yeah, basis may be different also. So, for example, we have discussed two bases on R2. So, are you able to see that? What are the? Uh, can you recall what are the bases for R2? I discussed in the last lecture.
There was a disk
Rectangle.
Rectangle.
and circle.
Exactly. So that is a rectangles and the circles. So two bases we can define for any particular topology. That is possible. So for the discrete topology, we already know that singletons are the sets, right? So singletons are the bases for discrete topology. Other bases I cannot remember now. Maybe we will see in the uh, upcoming lectures if there is any basis. But this example, what we discuss is the singletons generate the topology. That topology is exactly the discrete topology. So that is the objective what I discussed for this particular example. So if there is no more questions, then I